Welcome to this comprehensive walkthrough of LeetCode problem number 104, Maximum Depth of Binary Tree. In this session, you will learn how to analyze a binary tree and determine its maximum depth using both recursive and iterative approaches. We will cover the problem statement, analyze various methods, discuss complexity, and provide detailed Python and Java implementations. By watching this lesson, you will gain the skills to recognize and solve similar binary tree problems in coding interviews, understand the trade-offs between different approaches, and learn how to explain your solution clearly to others. Let's dive in. Let us go through the problem statement for LeetCode problem number 104 in detail. The task is to compute the maximum depth of a binary tree, where the maximum depth is defined as the number of nodes along the longest path from the root node down to any leaf node. Let's examine the examples provided to solidify our understanding. For example 1, we have the input tree in level order as 3, 9, 20, null, null, 15, 7. Visualizing the tree, the root node is 3, which has two children, 9 on the left and 20 on the right. Node 20 has two children, 15 on the left and 7 on the right. The longest path from the root can be either 3 to 9, or 3 to 20 to 15, or 3 to 20 to 7, all of which are 3 nodes in total, so the output is 3. In example 2, the input is 1, null, 2, meaning the root is 1, and there is no left child but a right child 2. The longest path is from 1 to 2, giving us a maximum depth of 2. These examples help you visualize how maximum depth is determined. There are a few additional important examples and constraints to consider for LeetCode problem number 104. Example 3 shows an empty tree, represented by, which should return 0 since there are no nodes present. The constraints for this problem state that the number of nodes is between 0 and 10,000. Each node's value can be any integer between -100 and 100. Let's talk about the edge cases. If the tree is empty, that is, root is null or the input array is empty, the function should return 0. For a tree with only the root node, such as input 1, the maximum depth should be 1. It is also important to consider heavily unbalanced trees, where all nodes are on one side, which would act like a linked list. The algorithm must handle all possible values within the given range. This ensures you can confidently solve the problem in any scenario. Let's talk about possible approaches for LeetCode problem number 104. The classic solution is a recursive depth-first search. For every node, you recursively calculate the depth of the left and right subtrees, and then the maximum depth is 1 plus the maximum of those two depths. This method is both concise and easy to read. However, recursion can hit call stack limits for very deep trees in some languages. An alternative approach is to use BFS, that is, a level order traversal with a queue, incrementing the depth at each level. This iterative strategy is safer when recursion might be limited and makes it easy to explicitly keep track of the current level. Both methods visit every node, giving the same time complexity. We will look at both approaches in detail so that you understand the different trade-offs and can choose the best for your situation. Let us compare the pros and cons of each approach. The recursive DFS solution is very straightforward and aligns closely with the way people think about trees. However, if you have a tall, very unbalanced tree, it could lead to a stack overflow in languages that have a small call stack limit. Iterative BFS avoids this risk because it uses a queue in the heap instead of the call stack, but it is a bit more complex to implement, especially if you're not as familiar with queue operations. The BFS approach also makes it easier to answer questions about the depth or content of specific levels. For most interview settings and competitive programming, though, recursion is preferred for its clarity and simplicity on LeetCode problem number 104. Now let's go step by step through the recursive depth-first search algorithm for LeetCode problem number 104. First, if the current node the root in the first call is null, you return 0 because there are no nodes below it. You use recursion to find the maximum depth on the left and right, then take whichever is deeper and add 1 to represent the current node. This naturally uses post-order traversal because the function is called on both subtrees before it uses their results. It's important to remember that the base case is when the node is null, providing the anchor for the recursion, At each internal node, you combine the answers from the left and right and propagate the answer upward. Continuing deeper into the implementation, the recursive approach typically fits in one short function. If you need to track more variables or annotate nodes, you might use a helper, but for maximum depth, it's not necessary. Switching to the iterative BFS version, you first handle the edge case of a null root. You then use a queue to process the tree level by level. At each step, you process all nodes at the current level, add their non-null children to the queue, and increment a depth counter. When the queue is empty, meaning all levels are processed, the final depth counter gives the answer. In Python, the collections.dec is preferred for queue operations because it provides constant time pops from the left, which a regular list does not. Here's the Python implementation for LeetCode problem number 104, both the recursive and iterative versions. The recursive function checks if the root is null and returns 0 if so. Otherwise, it recursively calls itself on the left and right child, adding 1 to the maximum of the two to represent the current node. The iterative BFS approach uses a dec as a queue, initializing it with the root. At each level, it processes all nodes in the queue, adds their children, and increases the depth. When the queue is empty, it returns the final depth. This code covers both primary solutions and is easy to adapt for similar problems. This is the Java implementation for LeetCode problem number 104. The recursive method closely follows the logic of the Python version, using the base case where the root is null to return 0. It then computes the maximum depth of both the left and right subtrees, adding 1 for the current root. The iterative BFS version uses a queue implemented with Java's linked list, processes each level, and increments the depth after handling all nodes at the current level. The main differences from Python are type declarations, method signatures, and explicit use of the queue and tree node classes. Both methods are efficient and work well for binary trees. Let's go through how the algorithm processes a tree step by step. Taking example 1, the tree is structured with root 3, left child 9, and right child 20, which has children 15 and 7. Starting at node 3, we recursively evaluate the left child 9, which is a leaf with both children as null, giving a left depth of 1. The right child 20 has children 15 and 7, both leaves, each with a depth of 1. Node 20 takes the maximum of its left and right child depths, adds 1, resulting in a depth of 2. At the root, we take the greater of the left and right depths, which is 2, add 1 for the root, and get a total depth of 3. Thus, the maximum depth for this tree is 3. Let's look at 2 additional step-by-step examples. First, for the input, 1, null, 2, the root node is 1, which has no left child, resulting in a left depth of 0. The right child is 2, a leaf node, giving a depth of 1. At root 1, the maximum of left and right depths is 1, and after adding 1 for root, the total depth is 2. For an empty tree, the root is null, so the output is 0. These walkthroughs confirm our algorithm correctly computes the maximum depth in both typical and edge cases for LeetCode problem number 104. Let's analyze the complexity for LeetCode problem number 104. Both the recursive DFS and the iterative BFS approaches visit every node exactly once, which results in an O of n time complexity, where n is the number of nodes. For space complexity, the recursive approach uses O of h space for the call stack, where h is the height of the tree. In the best case, where the tree is balanced, this is O of log n. In the worst case, such as a completely skewed tree, it's O of n. The BFS method uses O of n space, because in the worst possible scenario, one level could hold up to n divided by 2 nodes. BFS avoids the risk of stack overflow, but may consume more memory. For most problems, recursion is your best choice, unless you need to explicitly manage depth levels or anticipate very deep trees. Let's discuss some helpful tips and common variations for LeetCode problem number 104. Some related problems include minimum depth of binary tree and maximum depth of N-ary tree. Common mistakes are forgetting to check for a null root, or confusing the concept of tree depth with tree height, or making off-by-one mistakes, such as not including the root in your depth count. To avoid errors, always test your solution with empty trees, single-node trees, balanced, and skewed trees. Practicing both recursive and iterative solutions will make you flexible and ready for interview follow-up questions. Remember to always be ready to discuss the time and space complexity of each approach, and use visualization when explaining your thought process to interviewers. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!